Let's take a look at exercise 23 from section 2.2. A circle has equation x squared plus y squared minus 3x minus 3y minus 3 halves equals 0. Find the center, radius, and intercepts of the circle and then sketch the graph. So we are going to complete the square on this. So let's do that. And when we complete the square, we want the x terms on one side of the equation and the y terms on one side of the equation, same side of the equation. And then we're going to add 3 halves to the other side because we don't want the constant on this side on the left side of the equation. We want variable terms on one side, anything that doesn't have the variable on the other side of the equation. Now, we are always adding on a perfect square to complete the square on x, and we'll also be adding on a perfect square to complete the square on y. And whatever we added to the left side of the equation, we also have to add that to the right side of the equation. So because I'm squaring, I can ignore the sign. I look at whatever, first of all, I make sure that the coefficients of x squared and y squared are 1. Once I have, if those were not 1, I would divide every term of the equation by those coefficients. In order for this to be a circle, those coefficients would have to be identical. So I would divide every term by whatever the coefficient of x squared and y squared was if it was not 1. And then I take half of 3 and square it. And I add that to the x terms. And since that's actually the same coefficient for y, I'm also adding the square of 3 over 2 to the y terms. And I've now forced this to be a perfect square, both of these expressions to be perfect square trinomials. Now, sometimes, however, these coefficients of x and y do not have to be the same, but in this case they are. All right, so this factors into the square of x minus 3 halves on the left with respect to the x terms. So the perfect square trinomial in x factors into the square of x minus 3 halves. And notice whatever the coefficient, the sign of the coefficient of the x term is, that's the sign that goes in this binomial. And I'm going to add to that the square of y minus 3 halves. Now, typically, these would not have the same constant in them. But in this case, since the x and the y term had a coefficient of -3, these two binomials have the same constant of -3 halves in them. And then this becomes 3 halves plus 9/4 plus 9/4. So on the right side, I actually want to square these out. On the left side, it helps me with my factoring to leave these written as some constant squared. Helps me to see what goes in the binomial factors. All right, and now all I need to do is to add these constants on the right. Now, the denominators are 2, 4, and 4. So the smallest number that each of these denominators divides into evenly is 4. So I want all of my denominators to be a 4. These two are already 4. I'm going to get a denominator of 4 here by multiplying the numerator and denominator by 2. So this is equal to 6 fourths plus 9 fourths plus 9 fourths. Now I can add, now that I have the common denominator on all of these fractional terms on the right side. 6 plus 9 is 24. So I get 24 divided by 4. So 6 plus 9 is 15, plus another 9 is 24. 24 divided by 4 is 6. Okay, so remember that standard form says this is the square of x minus h plus the square of y minus k equal to r squared. Remember, r has to be positive. So my h then is 3/2, and my y is also 3/2. So remember, h and k are what you're subtracting from x in this parenthesis once you've written this in standard form. And what you have, h is what you subtracted from x, k is what you were subtracting from y. Now notice r squared is 6. That means r has to be the square root of 6. Normally, if we applied the square root property here, we would get r is plus or minus 6. But since we know r has to be a positive number, we discard the negative square root, and only the positive square root applies. So our center is the point 3/2, 3/2. And our radius is the square root of 6. Now to find our x-intercept, I let y equal 0. Okay, so to find the x-intercept, I let y equal to 0 and solve for x. So I have x minus the 3/2, that quantity is squared, plus 0 minus 3/2 squared. Remember, I'm replacing the y with 0, equals to 6. So that was my equation. So I have the square of x minus 3/2 equals to this, plus the square of negative 3/2. 0 minus 3/2 is simply negative 3/2, equals 6. So the square of x minus 3/2 plus 9/4 equals 6. And I'm going to rewrite, I'm going to subtract 9/4 from both sides. I'm going to use the square root property here. So I want what I'm squaring isolated on one side of the equals. And I'm going to write 6 as 24/4. going to subtract 9/4 from that, which 24 minus 9 is 15. So I get 15 over 4. So the x-intercepts then occur when x minus 3/2 squared, and I'm going to use colors here, is equal to 15 over 4. Now the square root property says I can lose that exponent of 2, which actually I don't need the grouping anymore since the exponent's gone, if I apply plus or minus square root to whatever's on the opposite side of the equation. So if I have a algebraic expression squared, and that equals to a constant, then I can lose the exponent of 2 if I replace it with, on the other side of the equation, with plus or minus the square root being applied to whatever's on that other side. So this is plus or minus the square root of 15 over the square root of 4. But the square root of 4 is 2. Let's add 3/2 to both sides, and x-intercepts are 3/2 plus the square root of 15 over 2, 3/2 minus the square root of 15 over 2. So in my math lab, you're going to enter these in and separate them with a comma. So that's one x-intercept. Here's the other x-intercept. Remember, the y's are 0 that go with those. Now the y-intercepts, I would do the same thing, except to find the y-intercepts, I'm going to replace x with. Okay, so to find our y-intercepts, we're going to do a similar thing. We're going to let x equal 0, and then we're going to solve for y. Now the nature of this equation is such that I hope you see this. So hopefully you see that we have the exact same thing we had, where when we subtract the 9/4 from both sides, when we do 6 minus 9/4, if we go back up here, 6 minus 9/4 is still going to be 15/4. And then notice I'm going to get the exact same result, except instead of this equaling x, it's going to equal y. Now normally that doesn't happen, but that happens here because the binomial squared in x was the same as the binomial squared in y. Normally that does not happen. So notice I get the exact same y-intercepts. So the y-intercepts are 3/2 minus the square root of 15 over 2, 3/2 plus the square root of 15 over 2. So we have the center, we have the radius, and now we are being asked to graph this. And so remember, and so one of the things we need in order to graph these is we need to approximate these values. So one of the things you have available as an MCTC student is the ability to download a student version of MyMathLab on your computer. And let's look back at the problem for a minute. And let's see what they told us. Oh, they want an exact answer, so we don't need to round this off. But we do need to get an approximation in order to know where to put these intercepts on the graph. So I'm going to use Mathematica. I'll let you know how to download that. And remember, these are our x and y intercepts. And so as we work various problems, I'll be showing you how to use Mathematica. So one of the functions you can use is a function that gives you a numerical approximation. So I'm going to tell it to give me the basic Math Assistant palette, and that's going to allow me to write these, to use a fraction template. And I have a radical template. Okay. So I'm doing a Control-C to copy that, and a Control-V to paste it again, and I'm simply going to change this to a plus. So this tells MyMathLab to give me a numerical approximation of this. And actually, I'm going to put this in braces. I have to give this as a set. All right, I'm going to move this Math Assistant out the way so I don't go off the screen. And I select this bracket on the right. I hold Shift and push Enter. And I only need this to the nearest tenth. So the smaller one is negative 0.4. And the larger one, larger y-intercept, and remember these are also the values of the x-intercept, is 3.4. So when you're approximating to put on the graph, you only need to go to the nearest tenth. So that basically tells me where to put those intercepts when I do my graph. So here I actually have all of this incorporated into a graph. Here is my center, the point 3/2, 3/2. Here's my larger y-intercept, 0, 3/2 plus square root of 15 over 2. Notice from the origin, that's 1, 2, 3.4, approximately 3.4 units up. It's exactly this. Here's that smaller y-intercept, which is negative 0.4 units below the origin. Remember, the x is 0 on the y-intercepts. And here's the smaller x-intercept, which is about negative 0.4 units left of the origin. Here's the larger, and remember that was exactly 3/2 minus square root of 15 over 2, 0. And here's the larger x-intercept, which was about 1, 2, 3.4 units right of the origin. And notice that's exactly 3/2 plus the square root of 15 over 2. And the y-coordinate when I'm at an x-intercept is 0. So in my math lab, you're going to be picking the graph that would look like this.